Okay, so in Section 3, Chapter 7, Section 3, we're going to look at what's called the natural base, which is the e. It's an irrational number. And this is actually a number that occurs a lot out in nature, so that's why it's the natural number. And it's often referred to as Euler's number. So, you'll see this around, especially when you get into higher math. There's a lot of things that involve e. So the formula for that is we let this value of n, this guy right here and this guy right here, we let those numbers run towards infinity and just get bigger and bigger and bigger and bigger. And as we plug larger values of numbers in for n, like a million, a trillion, a super trillion, trillion, what happens is that number settles into e, which is about 2.718281828, and it's a non-ending, non-repeating decimal. It's a constant, like 5 or 6, or an even better choice would be pi. It's very similar to all of those things. So we treat it the same. And when we're doing our math, like if we have a question that says, for example, e squared times e to the 5th, if my bases are the same, in this case they are both e, then I write down my base. Since I'm multiplying, I add the exponents. So the answer to this is just going to be e to the 7th. And you won't need to punch that into your calculator. This part's fine. The next question says, like 12 e to the 4th over 3e to the 3rd. Well, 12 and 3 can reduce. And so when I look at those guys, the first thing I need to do is write down a 4. They reduce. And then my base is e. That doesn't change. But if I divide now, when I'm dividing, I subtract my exponents. So now I'm going to have just e to the 1st power, which we very seldom write as e to the 1. We just usually will write it as 4e. On the last guy, this 2 on the outside is going to multiply with all of the exponents on the inside. So remember, this is 5 to the 1st power. So what I'm going to end up with is 5 squared e to the negative 6x. Okay, and so how does this change? Well, this is going to be 25 e to the negative 6x. Now, the only thing that has a negative exponent on it is e. That's it. So that moves to the denominator, and I end up with 5 over e to the 6x. So there's using some basic properties with e, the natural base. Okay, so the natural base functions. Now we can graph these bad boys, and the functions have this form right here: y equals a e to the rx. Okay, so if a is greater than 0 and r is greater than 0, then you have exponential growth. If a is less than 0 and if a is greater than 0 and r is less than 0, then you have exponential decay. So what does that look like? Well, on our exponential growth function, remember anything to the 0 power is 1. And if you've got your calculator handy, you can graph some of these things. But you'll need your calculator, and you'll need to find the e on your calculator, which should be its own button. And so if you go to 0, anything to the 0 power is 1. And then when you put 1 in for x, you're talking about e to the 1st power. So when you put 1 in for x, you're going to get 2.718. 2.718. So it's going to be right here. And it's going to be exponential growth. So it's going to look something like this. And that line's just off just a little bit. I wonder if I can... There we go. Look at there. Perfect. Okay. So there's your exponential growth, and it just takes off. And notice that on this particular guy, r is 1, so the number in front of x is 1. That's greater than 0. And a is 1 because there's only one e. Okay. So over here, this is exponential decay. Well, it's going to be very similar. We still have to go through the point 1, but now instead of going through the point, I'll just label this as a 0, 1, and 1, 2.718. So now we still go through 0, 1, but now we're going to go through the point 1. Let's move this guy over a little bit. We're going to go through the point 1, 0.368. Okay, and the reason we're doing that is because now we've got that negative value for x up here. So we're not doing y equals e to the negative x. We're actually calculating y equals 1 over e to the x. And so now my graph is going to look like this. Okay, and this is decay. And so these are your two parent functions. And again, if we look at this guy, our r is -1 and our a is 1. There's only one e, but my x is negative. So these are how our functions would look. Okay. All right, so let's look at some graphs here of exponential functions. And right off the bat, we want to find a and r. And a is that number in front, r is the number up top. So my a in this case is 3, my r is 0.25. So this is a growth function. Okay, they're both greater than 0. And what we're going to do is we're just going to pick a couple of points. I know that the growth function, the exponential growth function, has to look something like this. Okay, and so I just need to find 2 points that will work. And the 2 points I'm going to pick the point at 0, when x is 0. I'm going to pick a point when x is 1. So when x is 0 and when x is 1. So when x is 0, I'm going to have 3 times e to the 0.25 times 0. Well, that's going to be 3 times 1. And 3 times 1 is 3. So at the point 0, 3, I have a point. And then I'm going to check when x is 1. So I'm going to have 3 times, or 3e to the 0.25 times 1, which is the same thing as 3e to the 0.25. Well, I don't carry around in my back pocket e to the 0.25 power, so I'm just going to punch this into my calculator and get an answer. And it comes out to be 3.852. So when x is 1, I'm at 3.852. And if you want to check another point, you can. But basically what we're going to have, we have to have a shape like this. We have to have a shape like this guy. So my graph then needs to resemble that to the best of its ability going through these 2 points. So I'm going to have something like this. Okay, exponential growth. Again, I'm not going to get out a ruler and measure things, but I want to see this point as clearly as possible, and I want to see this point as clearly as possible. Alright, then on the other side, I'm looking at a is 1, but now r is -0.75. So what I'm going to do is I'm going to graph e to the -0.75x. I'm going to graph this. And then notice that I'm subtracting a 2 here. Well, this is going to move me just like it did with the other functions that we've talked about. If I do it to x, I do opposite of what the sign says. So I'm going to move 2 units right from my original function. And then this guy over here, this 1, this is going to tell me how I move my y coordinates, and they're all going to go up 1. Okay, so I'm going to graph my parent function in green, and then I'll move everything after that accordingly. Okay, so I'm looking at e to the -0.75. Again, I want to let x equal 0, and I'm going to let x equal 1. And keeping in mind that my decay function has to look like this. Okay, so when x is 0, I've got e to the -0.75 times 0, which is 1. -1. No, just 1. And so I need this point right here, and that's going to be the point 0, 1. And then when x is 1, again, you'll need your calculator. So I'll have e to the negative 0.75 times 1. So punch that into your calculator. And that's going to be 0.472. So at 1, I'm at 0.472. And so my graph for this guy is going to look something like this. Okay. So if this is my graph, then what I'm going to do is I'm going to just trace it real quick. So if I trace my graph right here, so here's my graph. And now what I want to do with this guy is I want to move it 2 units to the right and 1 unit up. So I'm going to grab that purple guy and I'm going to move him. Whoa. I want to move him 2 units to the right, 1, 2, and 1 unit up. And so there's my new graph. And notice this point right here, this guy right here is going to go 2 units to the right and 1 unit up. 2 units right and 1 unit up. Okay? And so the whole graph moves the same way. You can punch it into your calculator and find a whole value in the table of points, or you can understand that anytime you add something to the x and add something at the end, it moves you left and right. Alright, so the last thing here in this section is talking about interest compounded continuously. And so we get this formula here, and this works for money that you're putting in the bank. And it's A, which is the amount of money in an account after t years, is given by the formula. A equals P to the RT. P is principal, R is interest rate as a decimal, T is time. Okay, so if we deposit, let's just set these guys up. If we deposit $4,000 into an account that pays 6% interest annually, okay, so I've got $4,000 times E to the 0.06. What is the balance after 1 year? So times 1. What is the balance after 10 years? So 4,000 E to the 0.06 times 10. And after 50, 4,000 E to the 0.06 times 10. Or I'm sorry, times 50. So to solve these guys, all you're going to do is just punch into your calculator and get a number out. There's no other way to do it. That E is too tricky of a number to try and do in your head. So just type in, I'll work on the after 1 year. So I'm punching in E to the 4,000, or 4,000 times E to the 0.06 times 1. And I get, after 1 year, I'm going to have $4,247.34. Alright, on the next guy, I'm going to take that same thing, and now I'm going to have in my numerator, or in my exponent, 0.6 times 10. Which is $7,288.48. And then one more time for my 50 years. And now I'm going to have 0.6 times 50. Which is $80,342.15. It's a really easy formula to use, and it's fun to mess with.